Hello everyone. In this set of videos, we are going to take a look at some concepts that have been encountered numerous times in the previous weeks, but are worth sort of spending a little bit more time on understanding in detail, right? They are a bit tricky. They are things that get down to really the interface between the hardware and the software, and strictly speaking, in order to get a full understanding of what's going on here, you really need to be doing an operating systems course. But this is not an operating systems course. What the goal of this course has from the beginning been to sort of see what are the things you need to, the parts of the OS that you need to understand in order to get the basic interface between custom peripherals and your software going, right? So nevertheless, as I said, you need to understand a bit more about how exactly the boot process proceeds, how exactly the OS takes care of memory management and so on. So we'll talk a little bit about that in this set of videos. So broadly speaking, the goals of these videos are to understand the complete boot sequence from power on to user space, right? What exactly do I mean by that? Hopefully you can imagine it's from the time that I switch on the power all the way until I am able to interact with the system, right? There are a few different strategies that are typically employed in the context of loading bit streams. Now obviously this becomes relevant only when you're talking about Linux on an FPGA platform. So far most of the things that we looked at were on a bit more generic, right? It was Linux on ARM processors, but of course we were talking about custom peripherals, right? And in fact ultimately that's our goal. We want to be able to add custom peripherals on the FPGA, attach them to the ARM processor through the AXI bus, write drivers for them. Now, how exactly do you get that bit stream loaded into the FPGA? At what point in time should you do that is something that we will be discussing. Virtual memory, physical memory, and the role of the memory management unit. Virtual and physical memory are things that I have referred to at multiple points during the various discussions of drivers and so on. We'll go a little bit deeper into some of that as well now. And DMA is something that we recently looked at. There are some special requirements when you are allocating memory for DMA, and how exactly is that handled by the OS is also something we'll look at. And finally, something that we have been doing all along throughout this course, right, which is basically cross-compiling the kernel, right? We basically have a build system, a host, which is typically an x86, either a server or a laptop or something of that sort. You may have some other machine, but I'm assuming that it's Linux, right? What you're doing is you're compiling a Linux kernel, but not to run on your own system. You're compiling something that will run on some other kind of ARM based processor, usually targeting something like the Z board or one of the Xilinx Zinc platform series, right? Now, as we already discussed, that means that you're cross compiling. You have a host and you're compiling a kernel, but the compilation, the kernel that you're compiling is not going to run on that host, it's going to run on another target device, right? So how do we do that? What are the different choices that we have for build systems is also something that we'll briefly touch upon. Now, a lot of this, as I said, is mostly going to focus on concepts. Don't really have too much by way of demonstrations over here. We already looked at some of these in practice in many of the previous videos that we have gone through. But again, things like, for example, build systems, I'll not be taking multiple build systems and actually going through the entire building process. My goal over here is more to sort of introduce you to the concepts, tell you that these things exist, and hopefully give you enough of a background that you can then learn more about it on your own. Okay, so let's start with the boot up sequence, right? What exactly do we mean when we say that a computer is booting, right? And this term booting is in fact play on words. It is related to a story from I think the 19th century or so about a person who was able to fly by basically pulling himself up by his bootstraps, right? And obviously it is meant as some kind of a parody or a satirical story, right? But the idea of pulling yourself up by your bootstraps is a very interesting idea, especially when we apply it to the concept of computers, because the problem that we are dealing with in the context of a computer is I need the computer to load some kind of program, right, and to get going and to actually have be able to execute sophisticated software and give me a nice user interface and so on. The problem is, where do I load it from? Typically I would need to load that from some large storage device which would have to be something like a disk or some other, maybe a SSD or something of that sort. Now, the problem is that those are themselves complicated peripherals. Even accessing a disk and loading data from it requires fairly complicated functions, right? So now how do you get all of this going? And essentially the process that we follow is almost like it reminds you of pulling yourself up by your bootstraps, right? You have some small piece of code which in turn loads a larger piece of code, which in turn loads an even more complicated a whole set of drivers as well as the user space and so on, and then finally you have a working system. Okay, it's not a very good analogy, but it's okay, the term stuck. So everyone talks about booting, and when you say booting, you understand what we mean. We basically mean how does a computer, after it's been turned on, get to the point where you can interact with it. So the boot sequence, as we say, essentially starts at power on, right, and goes all the way to user space, right, and we have a number of different steps that we proceed through in the process of getting there. Now, the first thing that we can say is a computer is a digital system. What does that mean? As far as we are concerned, what matters is that when you switch on a digital system, you have two kinds of components in the digital system. One are the combinational logic gates, and the other are the sequential logic elements or the flip-flops, right? Now, combinational logic, when you switch on fresh, right, doesn't have any particular behavior. It just depends on whatever input it sees, and that's what you're going to see at the output. Sequential logic is different. What sequential logic does is that you have a clock, and only when the clock signal changes does the sequential logic basically update. Okay. Now, as soon as you switch on the system, the interesting thing is even the clock signal is not present, because even that is usually generated through a crystal and then put through a phase lock loop and so on in order to generate the appropriate frequencies. That takes a certain amount of time, which means that as soon as I switch on my computer, not even the clock is ready. Okay. What is usually done at that point is we introduce a new special signal called a reset signal, which just using some kind of very simple electronic circuits, probably even just an RC delay or something like that, we make sure that the reset signal is held at a certain value for a certain amount of time. Now, the good news is all our flip-flops have the ability that if I give it a reset signal, I can force them to either a 0 or a 1, a known state, in other words, right, that overrides the clock signal. So what is done usually is we take this power on, in fact there is something called the power on reset, right, and that signal is responsible for bringing one particular register inside the CPU to a known value. Well, it probably initializes most of the registers inside the CPU, but one of them is important. The most important one is what's called the program counter, right. So if I can basically initialize the program counter to a known value, and I then set up my digital hardware in such a way that at that address, in other words, if that address goes out onto the address bus, whatever is going to come back in response, right, because after all it's going to be performing a read operation, whatever comes back in response to that read operation should be valid instructions. How do I ensure that? I use something called ROM code. ROM stands for read-only memory, right. So what we do is that the person who has either designed the CPU or is designing the board, right, in most cases designing the CPU itself, sets up a specific type of ROM code whose job is very basic, right. It does some kind of initialization, and by initialization I mean not even things like disk or not even DRAM, right, which turns out to require fairly sophisticated initialization. The kind of initialization we are doing over here is for the registers or the chips that actually drive our power supplies and clock chips. Okay, so basically set up the clocks, set up the power supplies, right. Nowadays even power management ICs, because power is ultimately what you would think of as an analog domain circuit, right, but the power management ICs have fairly sophisticated digital control. They can be programmed to generate different kinds of voltages, they can be programmed to different current settings and so on. So that the PMIC or power management IC needs to be brought up in a certain way, which means that I need to be able to do that kind of programming and at least initialize it, right. Similarly, maybe for the PLLs to just get some clocks going and so on, but very basic, and its main job is to load something else called a secondary program loader, right, or the SPL. Now this SPL is what we call a very minimal kind of a bootloader, right. So you can see this sequence that's happening. We have got a very small program, the ROM code. The interesting thing about it is it's what's called immutable code, and what we mean by immutable means that it cannot be changed, okay, which is good. I typically want to make sure that I'm guaranteed that anytime I switch on the system, it is going to start reading from a certain location in memory, and I shouldn't be able to change that even if I want to, right, because it's possible that if I accidentally go and write some wrong instructions in that code, my chip is forever dead, right, there's no way I can recover from it. So the ROM code is immutable, and what it does is it typically loads the secondary program loader from either flash memory, which is the most common, or some kind of potentially the SD cards, right. Now you may think that's it, okay, why not just load the entire kernel and be done with it. The problem is that the ROM code is very small. It's probably on the order of like a few kilobytes, right, small number of kilobytes. So it can't really have any sophisticated drivers even to sort of, at best it can read from a simple peripheral, but not really do much more than that. So what it does is it loads the SPL. The SPL is a minimal bootloader which does a few more important things. One of the most important things it does is basically initialize the DRAM, right, and it turns out that the DRAM, which we all take for granted, right, as being this large gigabytes of memory that's present in our system, is itself a fairly sophisticated electronic subsystem. There are a number of parameters you need to write, right. There you might have seen that there are things like the strobe sequence parameters, the various timing parameters associated with the DRAM, which actually need to be set up properly by writing to certain registers, right. And if you don't do that, the DRAM is probably not going to respond the way that you expect, because it has to be tuned for the specific bus and the system on which it has been connected. There is typically some kind of a calibration sequence through which the DRAM also establishes at what speed it is able to work and so on, okay. Now it does all of that, and then it loads something else called U-boot. We'll get to this in a moment and talk a bit more about what U-boot is. But U-boot is, you can think of it as the next stage of the bootloading process. Its job is basically to load the actual kernel, right. So in all the demos that we have been seeing so far, there is this file which we call VM-Linux, right, which is an ELF file. It is in the extensible linker format. It is a compiled file which actually has information about where is the code, where is data being stored. So it has all the structure that we expect already of a proper executable, right, which means that I can't just put it somewhere in memory and expect it to work. I need something that will actually load it into memory properly. Now in our Renault demos, we saw that we would basically say load ELF, and it would take care of taking the ELF file and putting it into appropriate locations in memory according to the code, data segment and so on. U-boot does that on real hardware, okay. So it loads the kernel into some appropriate locations in memory. It also loads the device tree, right. And one more thing which we have mostly skipped in most of the Renault demos but exists in most systems is something called the init RAM, right, or the init RAM FS or the init RAM disk, which is the initial file system which contains some very basic kinds of files that are required for the system to come up, right. So all of these are loaded into memory by U-boot. It also passes any command line arguments that you might want to pass to the kernel, and then basically jumps to the starting point of the kernel. Now that kernel will basically say, okay, this VM-Linux that we saw was an uncompressed form of the image. Mostly you don't use VM-Linux directly, it is compressed and then stored because so that it can occupy less space, right. So the first thing that the kernel does is decompress that. It then goes and parses the device tree, and then based on the device tree, it now has enough information that it can start to probe for the different drivers. So when you boot a Linux system and you start seeing those messages there, the kernel has already taken over and is printing those messages. Now at the very end of that boot process, we had one /sbin/init file that we were creating and putting into our initramfs, right. That is the very first program that is executed by the kernel, right? And the expectation, the kernel basically expects a certain file to be present /sbin/init, right? And it looks for that, and if it finds that file, it will basically execute it, meaning that it will load it into a certain location in memory, because by now the kernel is like a full blown operating system, right? It has all the functions that are required to say, okay, how do I take an ELF file and load it properly into memory, right? So it loads it into memory and then jumps to the start of that init process. That is what we call user space. So this is essentially the sequence of steps that happen from the time that you switch on your machine to the point that it is actually interactive, right? You can actually probably type commands, assuming that init was something like BusyBox, which actually allows for interaction, okay? If it's not and it's a completely embedded system, you can also have an init which just does one particular task and nothing else,